Hi, this is Bradley Bush with another algebra video for you. If you are new to my channel, welcome. I'm happy you're here. If you're returning, thank you for coming back. If you find the content helpful or enjoy it, please subscribe to the channel, give me a thumbs up, or leave a comment. Today we're talking about introduction of sequences. Sequences are used all over the place, and they're kind of a fun topic. Our to-do list, well, first we'll talk about what is a sequence. We'll talk about two types of sequences, infinite and finite. We'll talk about recursion formulas, and throughout there are many examples. So here we go. First question, what is a sequence? A sequence is an ordered collection of objects, and a sequence contains terms or elements, and it's okay to have repeats. In math, sequences are also defined as functions. Here are the two types of sequences we'll discuss: finite sequences and infinite sequences. Infinite sequences, their domain is the entire set of real numbers. So in other words, 1, 2, 3, and on up, never stopping, forever. And so that's the domain, the x value, or the input. The output is the actual term of the sequence itself. And there are an infinite number of those as well. If I took that infinite sequence and I just took, let's say, the first n of them, like the first 5 or the first 20 or the first 1,000, and I stopped there, then I would have a finite number of elements in my sequence. That would be called a finite sequence. And the domain would be the first n natural numbers, so 1 through wherever it stopped. And then I would just have the y values, or the terms that are associated with those natural numbers, those inputs. Here's your official definition of a sequence. So an infinite sequence is written like so, with curly brackets, and then you have the name of the sequence. Here we call it an, or a sub n. A sub n is the general term, and we use that as shorthand to represent the entire sequence. And the fact that I have the curly brackets tells me it's a sequence. So an infinite sequence is a function whose domain is a set of positive numbers, as we discussed, and the function values, or the terms, are represented by these letters: a1, a2, a3, and on up. There's an, which is the nth term, and it just keeps going because this is an infinite sequence, so it never stops. So when we put them into functional form, we'd have ordered pairs, right? We'd have 1 and then a1, 2 and then a2, 3 and then a3, and you keep going forever. So sequences whose domains are the first n positive integers are called finite sequences again. So this is a little more rigorous in our definition. So we refer to the nth term of a sequence, and again the sequence has curly brackets. We refer to the nth term as a sub n, and we often write the sequence in a shorthand by writing out the general formula for the nth term. And it looks kind of like this. It'll be a sub n for the nth term equals, and then it'll have some function involving n. So let me give you an example. Here's an infinite sequence, and here's the general term. A sub n equals 3n plus 4. So all we do to find the elements of the sequence is we replace n with 1, 2, 3, 4, and we just keep going. We obviously can't write all of them because there's an infinite number, and that would be impossible, so let's just write the first 4. So literally, I am just copy and pasting like you would on a computer. If you took that right there, I just circled, a sub n equals 3n plus 1, and copied it, and then pasted it 4 times, all that would change would be the colors, because the colors represent what n is at that step. So the first step n's 1, so that n changes to a 1. The second step, n is 2, so n changes to 2. But everything else is the same. You see the 3 times something plus 4, 3 times something plus 4, 3 times something plus 4. It's all the same. So nothing changes. That's why the general form is so useful, because nothing changes except the n. Everything else stays the same. It doesn't matter which term you are on. Everything's the same except the n. So then we just do the algebra. So the first one, we have 3 times 1 is 3, plus 4 is 7. The second, when n equals 2, we have 3 times 2 plus 4, which is 10. When n equals 3, we have 3 times 3 is 9, plus 4 is 13. And when n equals 4, we have 3 times 4 plus 4, which is 16. Our first 4 terms of this infinite sequence then would be, curly brackets of course, 7, 10, 13, 16, and it would just keep going. And the functional form of that, we would add the domain. We would add the x. So we have a kind of like an ordered pair for each of these. 1, 7, 2, 10, 3, 13, 4, 16. We could make a finite sequence of this, say, because there are an infinite number of them, right? Say we only wanted the first 3 terms, or we just took the 3 first terms, and we just put them by themselves. So we just have 3 terms. Here would be our sequence, our finite sequence, a1, a2, a3. And then if we wanted to write it in functional form, we would have the 3 ordered pairs. So that's our first example of an infinite sequence. It's not too bad, right? It's the notation might be a little new for you, but it's not bad. Here's another example. This general formula is a little more complicated, but again, it really isn't bad. So our general form, a sub n, is a fraction. In the top, we have -1 raised to the nth power. So something that's interesting here, though, is when n is odd, -1 to an odd power is -1. -1 to an even power is +1. So our sequence will be alternating in sign. And then at the bottom, we have 3 to the n power, and then we have a -1. So the -1 is not in the power. So we have 3 to the raised to the n power quantity, and then -1 afterwards. So again, if we just took this general form and copied it and then pasted it 4 times here, we're just going to do the first 4. This is an infinite sequence, so the terms go on forever. That's what the ... means in the top right. But we can't obviously write all of them. But we'll just show you, for example purposes, we'll show you the first 4 terms. If I copied it and pasted it 4 times, I would just have these 4 instances. And the only thing that would change would be n. The only thing that changes is n. That's a great thing about these sequences. They all stay the same. Everything stays the same except the n's that I just highlighted in blue. And whatever n is in that step, that's what n is. So when n equals 1, all of my n's change to 1. When n equals 2, all of my n's change to 2. And it goes on and on. When n equals 3, they change to 3. When n equals 4, change to 4, and so on. And then after that, we just do the arithmetic. So once we've copy and pasted and changed the n's, we just simplify. So -1 to the first power is -1. That gives me -1 here. And then 3 to the 1 is 3. 3 minus 1 is 2. So I have -1/2. There's my first term. There's a sub 1. For a sub 2, we get -1 squared, which is +1. And then 3 squared minus 1 is 8. So I get 1/8. When n equals 3, I get -1 to the third power, which is -1. And then 3 cubed minus 1, which is 26. And when n equals 4, I get -1 to the fourth power, which is +1. And then 3 to the fourth power minus 1, which is 80. So I get 1/80. There we have the first 4 terms. We can write them out like this within curly brackets, -1/2, comma, 1/8, comma, -1/26, comma, and -1/80. And they would keep going, right, forever, because this is an infinite sequence. We could also write down their functional form just by including the ordered pairs, the 1, comma, -1/2. And then the second one would be parenthesis 2, comma, 1/8, parenthesis, and so on. If we wanted to take, say, the first 4 terms only, not all of them, we could create a finite sequence. And I have that sequence here below. which looks exactly like the infinite sequence. It just stops at a finite number of terms. So here we only have 4 terms, period. That's it. Let's chat about recursion formulas. Recursion formulas are kind of fun, especially once you get into things like computers, computer science, and coding, because recursion formulas are great for computers. We can also write sequences using recursion formulas, and a recursion formula is a formula that defines the nth term of a sequence as a function of the previous term. So let's talk about that for a moment. If, for example, n happened to be 5, then n minus 1 would be 4, and n minus 2 would be 3, and n minus 3 would be 2, and so on. So whatever n is, you could back up by doing n minus 1 step. That would back up 1 step. You can back up 2 steps by n minus 2, back up 3 steps by n minus 3, and so on. And the cool thing is, what if I change this? What if I said n happened to be 4? Then my n minus 1 would be 3, my n minus 2 would be 2, and my n minus 3 would be 1, so on. So the n minus 1 could reference a lot of different terms in the sequence. It just depends what n is. So once you fix n, then you can go back or forward accordingly from where you start, from wherever n is. So that's good to keep in mind, because n isn't a specific number. N changes, and whatever n is, n minus 1 is just the one before it. That's it. So if I wanted to find the first 4 terms of the sequence, which included a1 equals 5 and the a sub nth term, which is 3 times n minus 1 for n greater than or equal to 2. So one thing you need to know is that to write a recursion formula, you need 2 things. You need the first term, and then you need the general formula. So here we give you the first term, a sub 1, and the general formula, a sub n. That's all you need for a recursion formula. And again, a sub n is the current term, and a sub n minus 1 is the previous term for whatever n is. So let's write out the first 4 terms. We know a sub 1. That's easy because they gave it to us, right? It's 5. So we don't need to do anything there. A sub 2, though, uses a sub 1 in it. So you take a sub 1, whatever it was, and you multiply by 3 and then add 2. So instead of having a sub 1 there, I'm going to put down 5. So 3 times 5 is 15 plus 2 is 17. Sub 2 is 17. Then, for the next one, we take a sub 2 and we plug in 17, a sub 2. 3 times 17 is 51. 51 plus 2 is 53. A sub 4. A sub 4 uses a sub 3, the one previous. So a sub 4 is defined as a sub 4 equals 3 times a sub 3, or the one previous, plus 2. A sub 3 we decided was 53, and 53 times 3 is 159. 159 plus 2 is 161. I better change that to black. There we have our terms. A sub 1 is 5. A sub 2 is 17. A sub 3 equals 53. And a sub 4 is 161. So that's how you'd find the first 4 terms of a sequence when the sequence is defined recursively. That's it. Thanks for watching. I hope you enjoyed it. I hope it was helpful, and have a great day.